Hey guys, so sorry again I couldn't be here today. I'm taking my dog to the vet. Hopefully everything turns out okay. These are just a printed version of what I have on Google Classroom. So the first thing I would honestly recommend is just to go to Google Classroom and copy this down. You could also just pause this video as I work through this, but you can go to Google Classroom at any point and this exact document is there. You can copy down and come back and forth, whatever. Okay, so I'm not going to physically write. I'm just going to talk through what we're doing in 10.1. So 10.1 is talking about proportions, but what we're going to start looking at is how we compare two proportions. So it's a two sample. We'll start with z interval, and then eventually we'll do z-test. So we'll do all of that today. So I do have some pages I recommend. You can always, again, pause and go read the book if you would like. But basic idea is instead of just looking at one p-hat, we're looking at how two different sample proportions compare to each other. So remember, the basic idea of a distribution is what are the possible values and how often do they happen. And so overall they create some sort of general curve if you looked at every single possible sample, right? If you have a bunch of different samples and you're looking at how they compare, overall you've got like millions and millions of little sample dots making up a sampling distribution. Okay, so what is the shape, center, spread of a sampling distribution? This is where we have this is part of our conditions, that normality condition. For proportions is where we did n times p, had to be greater than 10. So the only difference now is it has to be true for both samples, right? So first sample, you have to do it, get your two numbers. Second sample, do n times p, n times 1 minus p. So it's the number of successes, number of failures for both samples have to be at least 10. And again, if you want to see more visuals and read more about this, I've got page numbers. The average of all the possible sample differences is literally just whatever the population numbers were subtracted. And then the standard deviation, remember this is like an extension of the idea of the Pythagorean theorem, kind of. So this was the sampling distribution, standard deviation, we call that the standard error formula, and then this is if you were combining. Even though we're subtracting the differences, no matter what you do, if you're combining two things together, it's going to have more variation, so you always add no matter what. And then this is where the other conditions come into play. So you have to have that randomization and independent or 10% condition, or this formula will not work. So again, there's the three conditions kind of at play. Okay, so this would be a good time again. If you want to try to pause it and do the formulas yourself and see how it goes, great. This is just working through a problem. So I'll let you guys handle that. So instead of looking at just one person's information, we're looking at both states and seeing how they compare. So I think that's all fairly self-explanatory. I believe in your notes I have this already in there for you so you didn't have to waste your time. So again, like I was saying above, you've got your same conditions as always. It's just now you have to check both samples. Check both samples, have to check both samples. So it's basically doing what we've been doing, just twice. Okay, so we got the basics. Let's do actual intervals. So I know I've changed the notes you guys have in front of you a little bit, so you might have to pick and choose. But here is your confidence interval formula. Okay, hopefully we can tell that that's a bit complicated. So I'm going to highly recommend you use the calculator instead of trying to do that every time, because that, no thank you. Remember, the formula chart only has like the has the vague version. You would have to fill all this in. So no thank you. Yes, please. Okay, so then let's go through a problem. Pretty sure I got rid of that on y'all's notes. Not a bad thing, just trying to save some space. Okay, so going through an example. The biggest thing here when you're reading through the problems now is you've got lots more to identify. So I really recommend as you read through the problem, you identify what is your first sample proportion and sample size, second proportion, second sample size, and come up with some way to label them. So on this one, we're talking about a 2013 poll versus a 2012 poll. So I use sub 13 and sub 12, whatever you want, but come up with some sort of system to keep yourself straight, because you would not want to mix match 0.38 with, like, actually this one doesn't actually matter because the sample size are the same, but in theory you wouldn't want to mismatch. Okay, so then going back to confidence intervals, we have not done that for a while. We've been doing significance tests. So remember, when you're doing your state plan, do conclude, big differences are in the wording of the first and last part. So now we're trying to estimate again. We're not answering a yes or no, is this greater than this kind of question. We're trying to estimate what is this actual value. So first of all, sample 1, or no, actually this is sample 1, 2012, had 25%. And then a year later, we had the same concept, but with 38%. So what this was talking about is why is it increased from one year to the next 13 points? It's not necessarily what's actually happening. Because of sampling, the fact this is not the whole population, it could just be that we got a very odd difference by chance. So what we're trying to estimate is what is the true difference between year to year. So you want to estimate, got your confidence level on there. Here's the fun part. You have to label both the population parameters. So if I'm using P13 and P12, I have to describe what both of those are. So P13 is the true proportion of adults dissatisfied with gun laws in, and I cut off, but 2013. And then what's nice is if it's the exact same thing, but in 2012. So here, you can always just do the little quotes to say that this whole thing is the same. Okay, so as long as you write it once, you can do this. Another way to say it is like P13 and P12 are the true proportions of adults dissatisfied with gun laws in 2013 and 2012, respectively. Something like that. Okay, so it's everything we've been doing, just kind of doubled. Okay, so then when you get to your plan, remember the thing we like to forget is we're doing you have to name the procedure, 2 samples Z interval. So now we're finally at our 6th, I believe it's our 6th type of inference. Checked all my conditions, make sure you're doing it for both everywhere. Okay, now on here, I actually did do the full formula. Again, I really recommend you use a calculator. So I'm going to go through that with you guys. So remember, it's down here at the bottom, stat. Oh, let me clear out my algebra stuff. Stat over to tests, and then we're doing 2 prop. I don't want a test, I want the interval. So 2 prop Z test, which is B. Click on it. So remember, we did this with the Pepsi and the Sprite and all that stuff yesterday. We're not actually putting in the p-hats, we're putting in like the number of successes and the sample size. So here's the tricky part about this, is all I have is the p-hat and the n value. And then the other thing to be careful of is the way I've labeled this is maybe a little counterintuitive. I put 2013 first, so make sure you're putting that in for X1 and N1, and then 12 would go in for the second one. Okay, so you gotta make sure however you set it up here, that's how you type it in here. Otherwise it's gonna make everything backwards. So here's the deal. I don't want 0.38, I want 38% of 111. So here's a nice little trick. You can just type that in, and then I want to say it won't work with decimals, maybe just round it. Sample size. You could always have done this in the normal screen too, so 253. You can always try it with decimals, but I'm kind of vaguely remembering that it doesn't like decimals. We were doing a 90% confidence. Okay, so I did this with the formula down here so you can see it. It's doable, it's just kind of annoying and nasty, but I ended up with this interval. Let's make sure this ends up being similar. So again, it's giving you the individual p-hats. Those pretty closely line up with that. It's got our sample sizes, 0.09, basically 6, which matches up. So yeah, that's pretty much the same thing. Much easier. If you're doing this, all you would have to do is label 2 prop Z interval and basically just put all that in your paper. Okay, and then we are 90% confident that the true proportion change or difference. All right, again, we're not talking about just one proportion, we're talking about the difference between 2. So the difference in the proportion of changed opinions is between these 2 numbers. So based on the interval, is it convincing evidence that the opinions have changed? Since 0 is not in the interval, yes. Because if it was truly no change from one year to the next, if I took the true proportion from one year and subtracted the true proportion from the previous year, it would be exactly 0. So since 0 is not in this interval, it does give us the indication that it has gone up somehow in the last year. Okay, so that is 2 sample Z intervals. Go on to Z tests, 2 sample Z tests. These get more complicated, so again, I'm going to highly recommend your handy calculator. Okay, so 2 sample Z tests. Again, you can kind of read through this. You get your two different sample proportions. Kind of going through the concept of there's two different explanations for why you could be getting two different numbers. Again, I'll let you guys read this, but one of them is kind of that you just happen to get two different samples by chance. Okay, so each school is the same and we just got different sample proportions by chance. So that's your null. So the assumption that we always go under is that one proportion always equals the other. Another way to write that is that the difference equals 0. So think back to the one we were just doing. We're always kind of assuming this is true. And then on this particular example, the other option is that they really are different proportions. So it could be that P1 really does not equal P2. And again, the other way to say that is the difference does not equal 0. So similar, you can say that however you want. Conditions, good news, same as confidence intervals. Some things to remember about not accepting the null. Here is what makes tests so much more complicated than intervals. We use what's called a pooled proportion. Basically, it goes back to the idea of power. You want to make the most powerful test you can. You want to make the most accurate rejecting of the null that you can. So it's to get a more precise estimate. I'm not going to go into details about what this is or why it is. Just know it's to make it as powerful as we possibly can. But basically what it is, instead of having two separate p-hats, we put them together. We pool our resources. Okay, so it's this formula here. So instead of having 19 over 80 and 26 over 150, we put 19 plus 26 over 80 plus 150. And I kind of put the two-way table in here again so you can kind of see what all these numbers up here were giving us. Just a little visual for you. But it's just taking the two sample proportions and putting them together and getting mega p-hat. So it's kind of sort of averaging these together, sort of. So it's not quite in the middle, but you can see that's in the middle. So we always assume the null is true. We're always assuming this is true, so we can put these together to make one nice big pooled proportion. And here's the fun part. That is the number you use when you're doing your standard error for tests specifically. So not to be confused when we did this with intervals, where we actually used P1 and P2. Once again, the calculator is so much better. You don't have to remember all this junk. But just be very, very careful if you're doing tests. We want to have the most powerful test, so we have this pooled proportion. And then when we get into our testing itself, we always found the test statistic and the p-value. So the test statistic was where in our sampling distribution do we fall, and then the p-value is looking at the area, the probability of that particular sample happening. Here is the formula for finding the boundary. Again, no thank you. I really, really, really want you to use the calculator. Please, 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 please. We need to get good at that now because it's just nasty. And it's gonna get nastier. Okay, so you find your test statistic and the p-value. Let's try a problem. So this is a fun little scenario. Are teenagers going deaf? The answer is yes. In a study of 3,000 randomly selected teenagers, so we have an older study, 15% showed some hearing loss, and then we do a much more modern, but still kind of old, test with less teenagers, so the samples is a little bit smaller, and we get 19.5. So kind of what we're going to test is this difference really significant? Okay, so again, your test, your null is that you're always assuming they're the same. So another way you could write that again is you could just write it like that. It's the same thing. I prefer this method because it actually gives you a number to look for, but it's the same thing. So here, what we're trying to prove is that, if we look here, evidence that the proportion of all teens with hearing loss has increased. Here's the thing you gotta be careful of. If I want it to have increased from the earlier study to the later study, P1 minus P2 being greater than 0 only makes sense if I say that P1 is the proportion of teenagers with hearing loss in the newer study, and then P2 is in the older study. Okay, if I flip-flop those, then I would have to flip that. I'd have to make it less than. So just be very careful. My recommendation with your two samples, this goes for any two samples, figure this out first. Label your P1, your P2, or however you're going to label them. Describe your parameters first, and then when you go back and figure out what this really means, you can figure out, do you mean greater than, do you mean less than, do you mean not equal to? This gets a little bit more confusing. So again, I recommend doing your parameters before you go back and try to figure out that. Okay. So this is the most self-explanatory one. Got your inference method. Got my 3 conditions. Again, I'm showing the formula work on all this. No, thank you. Yes, please. So I'm going to do this with you guys with the calculator. So we got stat, tests. Now we're doing the 2 sample or 2 proportion z-test. So we want number 6. Okay. Click on it. So same idea as the last one. Now this one's transferred the stuff from the old problem. I don't want that. So sample 1, again, go to how you've labeled it. So I'm talking about the more recent test. And I again made this table down here for your convenience, but you could always go back to the problems they gave you. So the first one was 0.195% of 1,800. There's 351 people, so that's basically what I did here to create this table. Don't have to make that table. Out of 1,800 people. And then the older study was 15% of 3,000, so that's 450 people out of 3,000. And again, the way I've just set this up, it's P1 greater than P2. So make sure you click on that, calculate. And so when I push calculate, if you come down here, I created the table just for convenience. I did that pooled proportion. I used that number specifically in the standard error part of this. Found the test statistic. Now think about the fact that you're always centered at 0 and you're going out by 1 standard deviation. Going all the way out to 4 is a crazy far distance. So the fact that the p-value ended up being a really, really small number makes sense. And then again, if you just did it over here, be careful because you got the same test statistic, 4.05, 4.05, but the p-value 2.6 is not the answer. All right, pay attention over here. It's really, 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 really small, which is another reason why I actually like doing the draw, because it'll show you the curve. And so if you're looking at this, wait for it, it's thinking. Got your sampling distribution, it gives you the z-value and it tells you 0. So I kind of prefer this. And you can also check, like if you ended up having the entire thing colored in, you know that you probably did the wrong, like you maybe did less than. So let me show you what happens if I accidentally do less than down here. So this is wrong. Don't do this. But this is a good indication. This is why I like doing this. If you get an entire thing colored in and your p-value is 1, you should think you did something a little bit wrong. So that's a nice little touch. I like this, kind of giving you a reasonableness check. Okay, p-value, super small. P is low, reject the null. We reject the null. We have convincing evidence that the proportion of all teens, remember you want to make, or the true proportion of hearing loss has increased from the older test to the newer study. Okay, and then just to bring it full circle with what we kind of talked about yesterday with experiments, between the 2 studies, Apple introduced the iPod. If the results of the test are statistically significant, which they definitely are, that is a huge significance right there, can we blame iPods for the increased hearing loss? And the only way we can do an actual cause and effect is with a well-designed experiment. And this was just looking at 2 random samples of teenagers. So, can establish cause and effect. It's possible that maybe car stereos are just too loud for those particular teens. Maybe they're going to a lot of movies and losing their hearing. Who knows? We can't narrow it down. Okay. I'll be back tomorrow to answer any big questions, and you'll have a small worksheet to work on. But if you finish this with some extra time, you can kind of chill. All right, I'll be back tomorrow. Bye.